and he's going to talk to us about phenomena from mega and giga.
So I appreciate being invited to come to this very stimulating workshop. There was a similar workshop about 5 years ago on attosecond that was at ITAM, and I went to that one. And it's very depressing to me that I used a variation of this same stupid joke back then. So I know it would have been understandable if it had been a good joke, but I ended up using the same dumb joke. But anyway, so mega and giga attosecond physics is, of course, picosecond, nanosecond timescales. The idea of the stuff that I'm going to talk about today is to maybe look back in the past when people were doing wave packet studies in the picosecond and nanosecond regime, and in essence just redo those calculations in the attosecond regime and see what differences and similarities are there. We've done a number of these kinds of calculations, and the ones that I'm going to kind of talk about today are going to be ones where you need 2 or more of the attosecond photons to get an interesting result. So the first thing that I'll talk about is this experiment done, and you guys might recognize a lot of the names here, over 20 years ago on basically hole burning of a Rydberg wave packet. The idea is that if you have a Rydberg state, it tends to absorb a photon when it's near the core, that Rydberg electron. And so if you have a visible light that has, say, a picosecond time scale, in essence, you can burn a hole in the wave function. You only absorb while the electron is near the nucleus, and so you deplete the wave function while it's near the core. And so you kind of make a hole in the Rydberg state. Now, a necessary thing that happens, if you think about it as quantum mechanically, is that if you have a hole in your original Rydberg state, it's not a stationary state anymore. And so what happens is you get a redistribution of that Rydberg state, say from 6s nd to 6s n plus 1 or n minus 1, variations of that. And so it's really a Raman effect that's being carried out through the continuum, right? So you kind of have to go up and then come back down to get there. Now, this was kind of an interesting experiment, and what they did show, and here in essence, was that you do get the redistribution amongst the states. It was sort of a little bit later experiment that actually showed that, in essence, the thing that was left behind was waving, right? That was actually kind of moving, that there was a coherent superposition of states that was there. And the experiment was done, as I said, by using an interferometric type of thing. But again, sort of the idea is you start out with a state, you hit it with a picosecond pulse, actually a couple, and you get a redistribution to nearby states. Now, there's actually something that I kind of glossed over in this. I said that this was like you're absorbing the photon when you're near the nucleus. Actually, both of these experiments were using a trick of barium, in that the barium in these Rydberg states have an admixture of 5d70 character up near, so up here it says n equals 26 or so. And in essence, what they were doing was they were depleting sort of the 5d70 character, and it was no longer really a stationary state. But effectively, it still was a hole burning. In some ways, it's maybe a little bit more correlation than just a radial packet, but that's sort of it's the same general idea. So you can imagine if you want to bring something down into sort of attosecond world, some variations on this that might be interesting to do, burning holes in like wave packets, electronic states. So for example, if you wanted to do just really the most straightforward one-to-one comparison, you want to make a radial packet, you can imagine what you might do is take something, say like calcium, and just hit it with something that has a bandwidth, and pretty much the idea is you have to have a bandwidth of your laser that is much bigger than the separation to the nearby states, right? I mean, it's just an energy time thing, right? So all that you really need to do is have something that has a bandwidth, say, bigger than 4 eV, and you'll get some kind of radial packet, say in calcium. Or if you wanted to do xenon, you have to have something essentially that has a bandwidth much bigger than 10 eV, right, to get this kind of thing. But there's other kinds of things that you can do with ground states that in some sense Rydberg states don't have, right? Rydberg state is just one electron, and outside of these special cases like with the 5d7d admixture, it's just a one electron thing. Whereas ground state kind of things will have, for example, correlation. So if you look at calcium, there's actually the calcium ground state, we say it's 4s squared, but it's really a mixture of 4s squared and 4p squared. Now, I haven't done the calculation, but I'd be willing to lay a fair amount of money on the line that the 4s character absorbs photons much better than the 4p squared character, right? Or the 3d squared character. So, in essence, you can monkey around with the admixture of the two different kinds of levels. And again, all that you would really have to do is beat the spacing, right, with the bandwidth. Now you can imagine also things in, say, molecules where you do things like to the highest occupied molecular orbital, you know, stuff like that. But since I don't know what molecules really are, I just kind of put together a whole bunch of words that seem to make sense to me, but might be just total gibberish. I'm not sure. But anyway, I think that that one would be a really interesting experiment if it actually made sense. So anyway, just to give an idea, so this was actually in the talk that I gave. Those few slides were in the talk that I gave about 5 years ago. What's new is that we actually went out and did some calculations in sort of the attosecond regime. So this was inspired by some correspondence with Ben and Bart. Some might say that Ben and Bart tricked me into doing the calculations, that those people are mean-spirited. So I had an undergrad go out and do some calculations. And just to kind of, I mean, we did calculations on things like the lithium 2s state or sodium 3s state. You get similar kinds of results, but in some sense, those results also, you need to kind of know what kind of model potential I was using and stuff. So I'm just going to talk about hydrogen. You start out in the 2s state. In some weird world, you might even imagine you can do this, right? Because the 2s state lives for about a second, so you can imagine making metastable hydrogen 2s and doing this experiment. Although you'd be insane, you get pretty much the same results for sodium and lithium. So the idea that I wanted to do, and the results that I'm going to talk about, is look at this Raman process. So you go up and you come back down. This is this kind of whole burning part of the wave function versus 2 photons up. So 2 photon absorption versus up and back down. Look at those two processes. They're both 2 photon processes, and you might expect that they behave similarly as you vary parameters. What we'd also like to do is look at, well, what happens if I, say, use a photon with, say, 1 atomic unit of energy versus 2 atomic units of energy, or 1.5 or 3. So what is kind of just generically depends on this process. And also, what happens to, say, the 1 photon part of the wave function. Now, clearly 1 photon doesn't depend on multi-photon bits, but what I mean is when you do 1 photon absorption, you've absorbed a certain amount of energy and angular momentum. What happens to that part of the wave function as you increase the intensity? So it's not really a 1 photon process. It's really sort of an admixture, say, of 1 and 3 and 5 and 7 photon processes. But what happens to that, in some sense, dominant part of the wave function? So we want to look at that. So let's start out just looking at the energy distribution of the 2 photon processes So the solid line is the part of the population that is left in total L equals 0, which is just, since it's one electron, it's just S-wave stuff. And the dashed, little rad dash curve is when you're leave the atom in L equals 2. So just so that you have an idea of the numbers, we just used 1 atomic unit for omega, so the photons have the energy of 27.2 eV. The field strength that we're using is somewhat high. It's about 10 to the 14 watts per square centimeter, but this is purely in the perturbative regime. If we double the field strength here, then these things just get basically a factor of 4 bigger, and they don't change shape or anything interesting. The width of the pulse was about 6 atomic units, so if you do like 6 times 25, you have about 150 attosecond wide pulse, right? So there's a couple of things that came up and that we kind of noticed and didn't, in some sense, either didn't think of it because we weren't clever enough, but were kind of interesting. I just want to point out. So again, this is the energy distribution, and this might look funny at kind of negative and low energies. What I mean by the energy distribution when you're below threshold is you just take the population of 2 neighboring states and divide it by the energy difference between those states. So that gives you sort of a population per unit energy. And the reason why I did that is we had sort of long discussions back and forth of how to present this. When you go to negative energy, I just wanted something that would smoothly connect from positive energy to negative energy, so you can see the whole energy distribution. One cute thing is this line right here is where the 2 photon absorption should peak, but it doesn't. Okay? And this is not a bug in the code. It turns out that there's a very simple explanation for this. And the simple explanation is that these peaks are broad. Photoionization and 2-photon ionization is a quickly decreasing function of energy. So if you take something broad that's centered right here, multiply it by something that's quickly decreasing, it shifts that broad thing to the left. So it's just simply the fact that it's easier to absorb low energy photons gives you a shift. And we saw that as we made these peaks narrower, they shifted up, and when you made them really narrow, they were sitting in the right spot, as you would expect. So that's one thing. Another thing that was a little bit of a surprise to me, anyway, is that we all have been taught about, how do you call it, the propensity rules, right? That if you absorb energy, you absorb angular momentum. But it's kind of interesting here that you've absorbed 2 photons and you have almost equal amounts of L equals 0 and L equals 2. So you absorbed energy twice, but you are just as likely to have absorbed angular momentum and emitted angular momentum as just absorbed 2. Conversely, when you look at this piece right here, the Raman back down, the L equals 0 part is just beating the snot out of the L equals 2 part. It's about 100 to 1 in population. L equals 0 to L equals 2. This is the piece, in essence, that makes the hole in the wave packet. Right? So this bit right here is the piece that is, in essence, the hole burning part of the wave function. So you're projecting onto the nearby states, okay, to get that bit right there. Okay. Interestingly enough, because the bandwidth is so large, the hole is projecting onto continuum states, which you didn't see in the Rydberg stuff, because in some sense when you project Rydberg states, you tend to go onto nearby Rydberg states. But here you're burning a hole in a very tightly bound state, and you get stuff that is actually a fair energy above the continuum. So these would be continuum electrons coming out. Right? Okay, let me go on to the next thing. The next thing that we wanted to look at was how do these probabilities vary versus time width. And one thing is that if you looked at the 2-photon absorption, and all that we did was in essence take and integrate up, or from here integrate down. It just said if you start from the middle and integrate down, that's Raman. If you start from the middle, integrate up, That's 2-photon absorption, that's the definition. As you make the pulse longer, the 2-photon ionization probability just keeps going up because the pulse is on longer. If you do it for the Raman part, though, it has a much more complicated behavior, is that it kind of starts going up and then it starts going down, right? And there's two ways of thinking about it, and they're really the same way. One way is just to say, as the Raman, the pulse is getting longer, there are not states close by that you can Raman back into, right? Because you have a certain spacing, right? And so that's why as the pulse is getting longer, the Raman process starts going down. And if you make the pulse really long, the Raman process would go away altogether, right? Another way to say it is that if you're burning a hole in the wave function, you better have turned off your laser before you had a Rydberg period.
This is just normalized for peak intensity?
No, the intensity is staying the same. So you're just making it longer. You just keep making it longer, right? So this is clearly what you would expect, right? Is that it's on longer, you just keep ionizing. This is maybe not quite so obvious, but even weirder is that this thing doesn't seem to be going to zero as you go down, but it's hard to even decide what you mean by going to zero width, because it's hard to know what you mean by Raman versus 2-photon absorption in that case. And this is what I meant before. As you made the peak, as you made the time width of the laser longer and longer, this is just the Raman part of the energy distribution. This gets narrower and narrower. It also gets taller, right? But what happens is eventually the getting taller part loses to the getting narrower part, and it starts going down. Okay? But this was, this was sort of what we expected. And the next thing that we did was we said, all right, let's look at the Raman piece, keeping the width the same, the width of the laser the same, but let's change the frequency of the laser. Okay? Now, we ended up taking a bigger width so that we can go from frequencies of 1/3 of an atomic unit, so 9 eV, all the way up to 2 atomic units, 54 eV. Now, just to give an idea of this, keeping the width of the Raman, keeping the width of the laser exactly the same, but changing the frequency of the laser, changed the amount of the Raman process by 4 orders of magnitude over that range. Because as you go higher and higher up in frequency, in some sense, it's harder just to absorb the photon, much less absorb it and re-emit and come back down. All right? There are 6 curves here, going from omega of 1/3 to omega of 2. And you probably can't see the difference between them because there hardly is any difference at all. So even though there's 4, so I just normalized them so that they're all at the same, they all have the same integral. And it turns out that it doesn't matter what frequency you use, the Raman process is the same. Which kind of, if you're thinking about it as a photon absorbed and a photon re-emitted, is kind of odd, because you would expect some kind of difference as you go higher and higher up in frequency, right? But if you just think of this as a hole burning, then the hole only depends on how long the laser is on. It doesn't depend on the frequency really at all. And that's why you have almost exactly the same energy distribution for those guys. All right, so that's looking at the Raman bits itself. So the question, the last thing that I wanted to look at for this system is now we're just looking in total L equals 1 in the energy range where you would expect 1 photon absorption, right? That line is where the 1 photon absorption really should give you. Again, it's shifted to the red for the same reason I mentioned before, that you're multiplying something broad by something that's decreasing quickly. And the red, the solid line curve is for a maximum field strength of 0.2, and then 0.4 and 0.8, and pretty much the intensities are about 1 10 to the 15 to about 2 10 to the 16. And you're going essentially from perturbative to non-perturbative. And I meant to, but I forgot to do this, force you to think what this should look like before actually showing you, but now I took that away. So I just normalized everything so that it's 1 at the highest point. But it has, the redshift, as I said, is what you would expect. But it has a behavior that, to me, is in some sense surprising, and I'm still not quite sure where it comes from. As I go up in intensity, I was expecting this energy distribution to change, right? Because, and you're going to get the interference between a 1-photon process and a 3-photon process, and something, by God, is going to change with that, right? And you do see a change. But it's in the opposite direction I was expecting. And the reason is I was expecting that if you're going to have a 3-photon process, 3-photon processes are going to be, well, it has higher powers of E, right, in it. And that means that the pulse, that part of the wave function, or that part of the interaction looks narrower in time because you're cubing it, right? And so if something's narrower in time, it should be broader in energy, right? But it goes the other way, it's narrower as the intensity goes up. So, now, one of my more cynical colleagues said, well, of course you should expect that it goes narrower because they're just interfering. And I just said, well, I'm not quite sure what that means, and we just laughed at that. But I have, as I said, I know what's making it, but I don't have a physical explanation for that.
It may be a bug in your code.
It may be a bug in the code, but we like to think that that in essence it's the same code that we've used so many times that it's probably not. So then the last thing that we did for this system is what does, oh damn, I did it in the opposite order again. But anyway, I wanted to look at the electron current as a function of time. So basically you just, we set in essence a detector out at 50 atomic units. That way the attosecond pulse is off before anything reaches our detector. We could have made it 35 or 40, but 50 is a round number because of our 10 fingers. But anyway, so we just put it at 50 atomic units. And we looked at what does the electron current look like at 50 atomic units for exactly the same field strength as before. There's a couple of things I should mention. You would expect it to come at about 950 attoseconds if you know the energy and stuff, but because of the 1/r potential, the electrons move a bit faster, so they get to this detector instead of about 950 attoseconds, it's about 900 attoseconds, right? So there's that. There is, though, if you look at the blue, kind of two weird things going on. So the first weird thing actually somewhat makes sense, right? Is that it's if you look at this at about the halfway point, the dashed line is somewhat narrower, right? So if you're having higher photon processes, it should be narrower in time, right? But as I said in the previous graph, it was wider. It was also narrower in energy, so that was kind of weird. But anyway, what also happens is that this blue, it's hard to see because of the huge scale here, the blue peaks 6 attoseconds later than the other ones, right? And in essence, this is also a little bit weird from the previous graph because I didn't mention it, but the higher one also shifted up in energy, and you would think if it shifts up in energy, it should come faster, but it's coming slower, right? But coming slower makes sense if you're burning a hole in the wave function, because the electron part that's still on the atom is taking time to come back to the nucleus to get absorbed. And so you're being delayed a little bit on the way out. It's not a huge effect on these scales, but it gets bigger as the intensity goes up. Right. So that's one part. The other part is of this talk goes back to something that I thought was really the coolest part of working with time-dependent quantum systems was looking at the time-dependent wave functions and how things like chirps and stuff like that come in. Because it was always just kind of fun to look at this. So what I'm going to show you guys is just a little movie first. back from my Rydberg, back from my misspent Rydberg days, of a two-channel system. So what you have to imagine is something like calcium. You photo-excite with a pulse laser to just below one of the thresholds so that there's, in essence, down here is you're going to be looking at the electron wave function as it escapes the atom. And up here will be the part of the electron wave function that's attached to the more highly excited state that's just going to give you a Rydberg wave packet. Right? And if you ask yourself, well, what's going to happen in this? It's pretty simple, right? If you're in the continuum, you absorb energy, and you have enough energy to go to infinity, and you just go. Right? You just keep going all the way to the detector. If you don't have enough energy, what happens is you leave the nucleus, you go out, and you say, my kinetic energy is dropping to 0, it's at 0, I can't make it. I come back to the nucleus, but when I come to the nucleus, I can exchange energy with the core, and part of me can now come out, right? So let me show you, it's kind of a cool movie. So again, the top part, so you can see up here, this is the electron has gone out to about the outer turning point for this guy. This little pulse is the direct ionization. It just goes all the way up. And you can keep your eye on it. But this part up here starts coming back, and when it comes back, it makes another pulse because this is the amplitude for coming out. And it's fun to watch because it will do it again and again. But what happens is that if you've ever played with this, Rydberg states aren't equally spaced, and so the wave function for the Rydberg disperses. Right? It just gets broader and broader. Right? And you can kind of see here, it's like this big smoosh out here, and down here you can see that it's just like some wobbly gorp. Right? Now, one of the things that we did was we kind of imagined, let's follow the electron all the way to the detector. So we just kind of put a box, and we just move the box with the speed that the electron is moving to look at the electron wave function as a function of time, just tracking it all the way out. For fun. As I said, this is my misspent youth in Rydberg physics. But before doing, all right, I finally remember. Before doing it, I want you to seriously think what these things are going to do. So this is the direct ionization peak. This is the part that came from the electron going out to the outer turning point, coming back, and then scattering into the continuum. This is the second one, and then you got this sparge down here, right? That's not looking like anything. So I want you to think, and you know quantum mechanically what happens, right? This is a continuum electron waves going out. So think about what you think would happen. Let's follow it. And it does this really, really weird thing. Let me show it again. So when I did this, I have to say, so this is like going to Hossein's comment, there must be a bug, or there could be a bug or something. When I first made this movie, I was like, all right, I screwed something up. Because what I know is continuum electron waves disperse. And what that means is the pulses get wider and they shrink, right, to conserve area, right? And you see that happening for this guy. But it does not happen for any of the other ones. And a weirder thing happens is that you saw that they get taller before they get broader. Right? So, as I said, this was like a week of my life trying to figure out what was wrong with this when it was right the whole time. But it actually is a very, very simple effect. It's kind of cool. That's why I'm talking about this in chirp. Why did I have this little thing under chirp? Right? And you have to remember, why do waves disperse? They disperse because their velocity depends on their frequency. And in continuum waves, your velocity gets higher as your frequency gets higher. Right? That's why you disperse. So this guy, this one at the front, is dispersing because what happens is it's made up of a whole bunch of energy components, and the higher components are moving up front. Why is this one first getting narrower and taller? That's because when you're on a Rydberg atom, it's the opposite way. Higher energy is lower velocity, lower frequencies. Right? This is just, why does the Earth have a longer year than Mercury? It's the same question. Right? So what happens when this guy comes out into the continuum, the low energy parts of the wave packet are out front. This thing is chirped when it comes out. And what happens is that it takes a while for the faster guys to catch up and then go through. Okay? So anyway, so that was in some sense just kind of for laughs and giggles, but it got us thinking a little bit about what could we do with chirps and looking at some various physics effects. And the other thing is that when you're thinking about chirps, a lot of times just a simple boneheaded classical way of thinking about it, once you kind of do it appropriately, gives you sort of the right answer. And it turned out when we went through this thing, where these things peak is exactly where you would expect them to peak in distance. It was kind of cool. Just it was a classical calculation. But I can't leave this before saying, one of the coolest things to me is that this spargy stuff down here that doesn't look like anything resolves itself into separate peaks later. So you think that there isn't anything on the atom that's saying it's coming back a third time. It's just a big smoosh of stuff. But the electron knows. When it leaves, it knows that whether it's come back 3 times or 4 times or 5 times. You can see it. So anyway, so what I'm going to skip over this. We are looking at both energy and angular probabilities for 2-photon double ionization of helium in attosecond kind of pulses. And what we wanted to do was we wanted to see how did the chirp of the attosecond pulse affect the results of the calculation. Now, if it was a 1-photon process, chirp doesn't do anything, right? I mean, it has to be a 2-photon or some kind of 2-photon plus 1-photon interference or something. It can't just be a one-photon process. Now, the chirp that we picked looks like this. So this eta parameter will tell us about the amount of chirp. The sign here tells us that the lower frequencies of the laser come earlier in time and the higher frequencies come later. All right, to make sure that you remember your helium atom, if you do 2 photons as a sequential ionization, if you first ionize helium and then you ionize helium plus we're doing these calculations at 91.6 eV, then what you should expect to see is 1 electron at 67 eV and 1 at about 37 eV. If you leave the atom excited in the 2s state, it actually flips around and you should see a 26 eV and a 78 eV. If you do a direct 2-photon ionization, not as a sequential thing, then the 2 electrons share about 104 eV worth of energy. So that's to give you the kind of scale of those things. So this up here is showing the 1 electron energy distribution. So you don't care what the other electron did at all. You just want to know what is the energy distribution for one of the electrons. So the one that I would like you to look at first is this black curve. So this is an unchirped 450 attosecond pulse. This stuff right here on the wings is leaving the helium behind in the 2s state. But these peaks are about where you would expect to have sequential double ionization. But there is some stuff in the middle that comes from direct 2-photon double ionization. This dashed curve right here is when you have a chirp in those units of 3.18. And that's kind of an interesting number because down here we also did a calculation with an unchirped pulse of 135 attoseconds. These are exactly the same frequency components. So it's just one is chirped and one's not chirped. And if you compare this red curve with this down here, you see that there's a big difference between them. Right? There's a lot more stuff coming out together than there is over here. So it looks like this lower frequency bit coming first for the attosecond gives you much more distinguishable peaks, and it looks much more sequential. And When you look at this really in 2 electron space, you find out that it is exactly like how you would have interpreted it. So this is the 1 electron energy and the other electron energy. If you have 450 attoseconds, they're clearly distinguishable as basically almost everything is coming from sequential ionization. When you have 135 attoseconds, it kind of still looks like sequential ionization, but there's a fair amount of stuff inside of here. And actually, there's too much stuff in here just to be an incoherent sum of something over here and something over here. So the fact that there's stuff in here is actually coming from the coherent superposition of those guys. If you chirp, and remember this one and this one has exactly the same frequency components, you get completely different looking 2 electron spectra. This completely looks like sequential double ionization, whereas this has a lot of direct double ionization. If you do keeping 450 attoseconds and look how it evolves as you make the chirp bigger and bigger, as you make the chirp bigger, these things get wider, but it really still just looks like sequential ionization. Which, and some of it's like, all right, there was a lot of calculations for something that in the end is what you would expect, right? Because if you chirp like crazy, then what happens is you have a really broad pulse. Well, what would you expect if you had a really broad pulse? You would expect to have an absorption and maybe a bit later another absorption. And so it's about what you would expect for those things. I'm out of time, but I threw these on here. So Tom was talking about this bit of exciting right to the threshold. So I just wanted to throw these slides in at the very end. Is that we ended up doing some calculations for exactly the same kind of thing Tom was doing, except instead of microwaves, we were using 800 nanometer light. And then you're exciting from the 1s. So this was all being done in hydrogen, hence my comment, from the 1s up to the near threshold regime.